In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 74. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with change in dielectric characteristics of transformer oil when subject to oxidation. As from the study, it has been exhibited that there would have a strong linkage between oil oxidation process and increase in its relative permittivity. Due to oxidation reaction in transformer oil, that would lead to the formation of carbonyl groups and other polar oxidation byproducts, resulting in an increase of oil's overall relative permittivity. It is as because these polar molecules within the oil would have the greater ability to align themselves with an applied electric field, thus increasing the dielectric constant and permittivity. However, an increase in the relative permittivity of transformer oil does not necessarily lead to a significant increase in its electrical conductivity. But the presence of carbonyl groups and other polar oxidation products in transformer oil does significantly increase the oil's electrical conductivity. These oxidation byproducts, which include acids and other polar compounds, would thus to increase the number of charge carriers in the oil, causing to enhance its ability to conduct electricity. Most important. The transformer oil is typically made from very pure, highly refined mineral oil, where its electrical conductivity would be a key parameter for assessing its quality. In IAC 60296-2020, were to recommend the electrical conductivity of unused and recycled mineral insulating oils for transformers, which should be as low as possible. The standard does not explicitly indicate a minimum value of the oil's electrical conductivity, but has categorically mentioned the maximum limit of 1.52 picosiemens per meter at 40 degrees centigrade, picosiemens per meter. Higher conductivity that indicates to more current leakages through the insulating fluid for a given voltage, causing to initiate higher conduction losses. The primary function of a transformer oil is to insulate high voltage electrical components, and for that purpose it is essential to require a low conductivity of oil. The electrical conductivity of transformer oil is a critical parameter which would have been further influenced by the factors like temperatures, contaminants, and presence of oxidation byproducts. Basically, there would have a significant relationship between the electrical conductivity of transformer oil and the rise in temperature. This is as because the mobility of charge carriers within the oil would have been quite enhanced with the rise of temperature. The contaminants in transformer oil, particularly those of a polar nature, can significantly influence in increasing the electrical conductivity of the oil. Polar molecules, as reduced in transformer oil due to oxidation reactions, would thus tend to dissolve more readily in oil than the non-polar molecules. These polar molecules would have the ability to carry electrical charges, increasing the conductivity of the oil. Oxidation reactions in transformer oil, especially under the most critical operational environment of having high temperatures and of being the electrically stressed conditions, then that would have to create various organic acids within the oil. The acids that are to be produced through the oil oxidation would be classified into two categories of organic acids. One, low molecular weight carboxylic acids like formic, acetic, and propionic acid, which are consequently have a greater impact on the paper insulation system. Number two, high molecular weight carboxylic acids like stearic acid and naphthenic acids, which are generally be less reactive with the paper insulation as compared to low molecular weight acids. Now, comparative study low and high molecular weight carboxylic acids. Low molecular weight carboxylic acids would have a relatively small number of carbon atoms in the molecule as compared to high molecular weight carboxylic acids. Low molecular weight carboxylic acids are inherently much more hydrophilic than that of high molecular weight carboxylic acids. It is preferably noted that the carboxylic acids with fewer than about 5 carbons is to be characterized as low molecular weight carboxylic acids, which would have been readily dissolved in water. Whereas the carboxylic acids with more than 5 carbons are often characterized as high molecular weight carboxylic acids. With having smaller molecular size and of greater polarity, the low molecular weight carboxylic acids are always being more attracted to the polar cellulose in paper insulation than to the non-polar transformer oil. Most important. It is as because the polar molecules are more likely to interact with other polar substances due to their inherent dipole moments, which lead to electrostatic attraction between oppositely charged ends of the molecules. While in case of nonpolar molecules, where they are being characterized by an even distribution of charge, resulting in lacking of significant charge separation. Such criteria has made more likely to prefer the nonpolar molecules readily dissolved in other nonpolar environments. Within the carboxyl group, that is COOH, where there would have significant difference in electronegativity between carbon, oxygen, and hydrogen. As per Pauling scale, as per Pauling scale, the electronegativity of the oxygen atoms is 3.44, and its value is always be higher state rather than that of carbon, that is 2.5, and hydrogen atoms 2.1. Understanding with the fundamental concept of electronegativity of an atom, where it refers the ability of that atom to attract a shared pair of electrons towards itself in a chemical bond. Therefore, electronegativity of the atoms would have to act as a key factor in determining the type of bond formed between atoms. In the carbonyl group COOH, where it contains a carbonyl group, that is C double bond O, and a hydroxyl group OH, attached to the same carbon atom via a single bond. As because of the higher electronegativity of the oxygen atom, that would thus to create an uneven sharing of electrons in the chemical bonds, resulting in a dipole moment of polar carbonyl group and a polar hydroxyl group. The combined effect of these polar covalent bonds has made the entire carboxyl group as of a polar functional group. Now see the format of the carboxyl group, where carboxyl group consists of a carbon atom double bonded to an oxygen atom and single bonded to a hydroxyl group OH. When this group is part of a molecule, the compound is known as a carboxylic acids. A carbonyl group COOH is thus to be composed of a carbonyl group and a hydroxyl group attached to the same carbon atom. Carboxylic acids are the carbon compounds characterized by the presence of carboxyl functional group. In carboxylic acids, the carbonyl group is responsible for the molecule's polarity and reactivity in undertaking various chemical transformations, while the hydroxyl group contributes to the acidic nature of the compound. Carboxylic acid, whose structural formula is R-COOH, where the symbol R is typically represented the hydrocarbon chain in a carboxylic acid. So, COOH carbonyl group refers to the carboxyl group. So COOH refers to the carboxyl group and R refers to the hydrocarbon groups of organic compounds consisting only of carbon and hydrogen atoms. See the formats. Carboxylic acids. The reactivity and acidity of a carboxylic acid would thus be characterized with the combined effect of the carboxyl group and the length of the hydrocarbon chain. The molecular weight of a carboxylic acid is the sum of the atomic weights of all atoms in the molecule, and it is rather to be noted that the carbon and hydrogen atoms in the longer hydrocarbon chain would have to contribute the most of the overall mass. As from the previous concept, carboxylic acids, which thus to configure with carbon chain of having more than 5 carbons, are often referred to as long chain carboxylic acids. Different types of carboxylic acids, especially those formed during transformer oil oxidation reaction process, would contain long hydrocarbon chains, that is alkyl chains, attached to the carboxyl group. A longer hydrocarbon chain would then to indicate that the chain has to contain with repeating units of carbon and hydrogen atoms, resulting in a higher molecular weight. High molecular weight carboxylic acids that include stearic acid and naphthenic acids. Stearic acid C18H36O2 is saturated fatty acid with an 18 carbon chain, which is thus to be considered a long alkyl chain, whereas naphthenic acids are a complex mixture of both cyclic and acyclic carboxylic acids with varying chain lengths and structures. However, the specific type of acyclic, that is straight chain carboxylic acids within the naphthenic acid mixture are being characterized as fatty acids with a long hydrocarbon chain, that is alkyl chain. Carboxylic acids are being categorized on various factors, including the number of carboxyl groups, the presence of other functional groups, and the length and saturation of the alkyl chain. Stearic acid and naphthenic acids both are being of the separate characteristics of high molecular weight carboxylic acids, which would have been formed during the process of oxidation reactions in transformer oil. Carboxylic acids are organic compounds characterized generally as polar due to the presence of polar carboxyl functional group COOH. The hydroxyl group in those carboxyl group can have the ability to form hydrogen bonds with water molecules, causing to make the carboxylic acids somewhat soluble in water. These solubility characteristics would have to decrease as the length of hydrocarbon chain attached to the carboxyl group increases. While the number of carbon atoms increases in carboxylic acids hydrocarbon chain, then the hydrophobic character of the alkyl group becomes more dominant, decreasing the overall solubility of the carboxylic acids molecule in water. That is hydrophobic character. Key points regarding high molecular weight carboxylic acids. Alkyl chains are typically composed of a series of CH bond, carbon and hydrogen bonds, and as the individual CH bonds are being non-polar, so the entire alkyl chain tends to be non-polar. According to the Pauling scale, the electronegativity of carbon is 2.5 and the electronegativity of hydrogen is 2.1. So, there would have a small difference in electronegativity, that is of 0.4 between carbon and hydrogen atoms within the chain. And that leads to the relatively even distribution of electron density, resulting in a minimal charge separation within the CH bonds. Each additional carbon and hydrogen atom in the alkyl chain that, that would add to the overall molecular weight of the carboxylic acids. As the alkyl chain in a carboxylic acid gets longer, then the nonpolar alkyl portion that would effectively start to counteract the polar nature of the carboxyl group. Due to the dominant influence of the nonpolar alkyl chain over the polar nature of the carboxyl group, that can affect the overall polarity of the molecule. Therefore, a long alkyl chain in a carboxylic acid can significantly reduce the molecule's overall polarity character as subject to the influence of alkyl chain's nonpolar nature and of larger size. The reduced overall polar characteristics within the carboxylic acids can significantly affect its various properties. A longer nonpolar alkyl chain in a carboxylic acid would have to contain more electrons, which would cause to create greater intermolecular attraction. Molecules of the stearic acid and naphthenic acids, whose presence can obviously lead to propagate stronger intermolecular forces within the transformer oil. But the specific type of strength of these forces would have to depend on their molecular structure and interactions involved with the oil. The specific structural configuration of atoms within stearic acid and naphthenic acids must have to influence how they interact with each other and with the rest of the transformer oil. However, such alteration and change of the overall intermolecular forces within the oil would thus to play a crucial role in affecting the oil's physical properties like viscosity, dielectric strength, and thermal conductivity. Consequential effect of low and high molecular weight carboxylic acids as formed during oil oxidation reactions. The low and high molecular weight carboxylic acids in transformer oil would rather to be produced through the prolonged oil oxidation process, but their presence in transformer oil would have to propagate some contrasting impact on the transformer's overall insulation and cooling cycle. It is to understand that the functionality and lifespan of a transformer must have to depend on the condition of the cellulose-based solid insulations, which include paper and pressboard. Hence, the life of the cellulose insulation is thus to be most critical factor to determine the overall lifespan of a power transformer. High molecular weight acids, which include stearic acid and naphthenic acids, are hardly soluble in oil and are not so much aggressive. Due to larger molecular size, these high molecular weight acids do not have significantly penetrate the cellulose-based paper insulation as readily as the lower molecular weight acids. Now, The solubility is always be influenced by the larger molecular size and stronger intermolecular forces. Diffusion is the movement of molecules of a region of higher concentration to lower concentration, and the rate of diffusion is affected by the solubility of molecules. As the high molecular weight acids are being less soluble in oil, so their molecules must have the lower ability to dissolve into oil, causing not to diffuse readily into the cellulosic part of the paper insulation. It is quite evident that the high molecular weight acids may not be directly involved in the acid hydrolysis of cellulosic part of the paper insulation. Acid molecules of larger in size, when to accumulate in the oil, would therefore have the greater tendency to aggregate and precipitate out of the solution, especially when the oil is subjected to degradation processes, resulting in issues like sludge formation. If those insoluble molecules that are to be deposited on the paper or other parts of the transformer, then that might cause to hinder the heat transfer process, leading to localized degradation and weakening of the paper. Low molecular weight acids of being relatively shorter hydrocarbon chains, where the polar carboxyl group would have to dominate their overall polarity. The carboxyl group, as it is polar, so this polarity makes a molecule more water soluble. But the shorter hydrocarbon chain in these acids that contributes a certain degree of nonpolar character, allowing it to interact with nonpolar hydrocarbon chains in oil. However, such interaction, though, would have been weaker than the hydrogen bonding that dominates their water solubility, but it is enough to allow for some mixing with the nonpolar components of the oil. The shorter hydrocarbon chain carboxylic acids like acetic acid or propionic acid would have the molecules of dual character, allowing them to be soluble in both polar and nonpolar solvents. Hence, low molecular weight acids, as being more soluble in oil, may diffuse more readily into the oil and potentially cause much higher consequential degradation effect on the cellulosic part of the paper insulation. Basic reasons there to be discussed. Smaller size of molecules and higher solubility in oil would cause to have an easier absorption into the cellulose, leading to accelerate the degradation of cellulose based paper insulation. Cellulosic part of the paper insulation is composed of a polymer made up of glucose molecules linked together. Each glucose unit in cellulose has several hydroxyl groups which are capable of forming hydrogen bonds with other adjacent hydroxyl groups. Low molecular weight acids, which include formic, acetic, and levulinic acid, also have to contain hydroxyl groups. The acid molecules and cellulose molecules, while would come in close proximity, then hydrogen atom of the acid's hydroxyl group can form a hydrogen bond with the oxygen atom of a cellulose hydroxyl group. Therefore, when an acid comes in contact with cellulose, then acid's hydroxyl groups can start to participate in hydrogen bonding with cellulose's hydroxyl groups. The hydrogen bonds as formed would be a specific type of intermolecular force and would have become crucial for molecular interactions. The particular interaction between acid molecules and glucose molecules within cellulose can indeed lead to the formation of a network of hydrogen bonds. This network of hydrogen bonds in cellulose significantly influences its physical and chemical properties by affecting its polymer structure, stability, and interactions with other molecules, particularly water and acids. In contact with the acid molecules, that leads to the hydrolysis of cellulose, that is acid hydrolysis of cellulose, causing to disrupt the hydrogen bonds that hold the cellulose chains together. Acid hydrolysis is a chemical process and through which that would have to degrade cellulose based paper insulation, causing to further produce low molecular weight carboxylic acids such as formic, acetic, and levulinic acids. Formation of these acids would therefore be the byproducts of the cellulosic degradation process, and that would contribute to further breakdown of the cellulose polymer chains, leading to a cycle of degradation and weakening of the paper insulation. However, these low molecular weight carboxylic acids would initially have to dissolve in oil before potentially reacting with it. The dissolved carboxylic acids, while starts to precipitate in various chemical reactions with the transformer oil, then that can lead to the formation of additional byproducts. However, the chemical interaction between the acid and the oil would have been influenced and further accelerated by the interim factors like temperature, pressure, and the specific chemical composition of both the acid and the oil. It is thus to understand that the low and high molecular weight carboxylic acids would have been initially formed in transformer oil through oxidation of oil and the hydrolysis of cellulose based insulating paper. These two, oxidation of oil and the hydrolysis of cellulose based insulating paper. If the formation as well as accumulation of acids in transformer oil would have become so high to exceed the solubility limits of the oil, then the acid molecules should have become less soluble and more prone to precipitating out of the oil. These insoluble carboxylic acids, particularly of higher molecular weight, can have to react with the oil molecules, producing a sticky semi-solid deposits known as sludge and waxes. Such formation of sludge and waxes is mainly due to consequential effect of their long hydrophobic hydrocarbon chains, which are nonpolar and water repelling characteristics. Water repelling characteristics would have to cause the insoluble molecules to aggregate and then to interact with each other through their hydrophobic interactions, leading to the formation of waxy solids and viscous sludge. There would have the possibility to accumulate sludge on the transformer's core, windings, and radiator pipes, causing to act as an insulator and severely hindering the heat transfer efficiency. So, accumulation of sludge and polar contaminants in transformer oil would have significantly lowered its dielectric strength, increasing the risk of electrical breakdown. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.